A language model can encode the fact you need and still fail to say it. Standard accuracy cannot tell whether the shelf is empty or the key is lost. VAKE builds an experiment where activating one explicit fact is the only thing allowed to change. Pre-training may encode a fact richly, while greedy decoding fails to retrieve it. Scaling helps storage, but does not guarantee a reliable route to the answer. VAKE treats factual question answering as an access problem and asks for a controlled test of activation. Ordinary chain of thought entangles three events: recalling a fact, reasoning with it, and producing an answer. When accuracy improves, we cannot tell which changed. VAKE separates elicitation from answering so the contribution of newly surfaced knowledge can be observed. Let a policy generate a query-conditioned knowledge increment from the question and insufficient context. Successful activation is model relative. The frozen answerer is wrong without the increment and correct after the increment is added. That wrong to correct transition is the operational definition. The intervention has two equations. The same answerer, question, and context first fail, then succeed when the inserted triples are present. The knowledge begins in policy parameters, but becomes explicit evidence, allowing its answer-enabling effect to be tested. Documents are parsed offline into a graph of subject, relation, object triples. In the main protocol, raw documents are never shown during training or standard inference. The policy and answerer see only a sparse retrieved subgraph, making each insertion discrete and inspectable. Question mentions are string matched to graph nodes, then retrieval expands two breadth-first search hops. Keeps the 5 most question-similar edges per hop, removes any triple containing the gold answer, and caps the union at 10 triples. The intent is a relevant Q set without a complete answer path. VAKE trains sequentially in 2 stages on the same question and subgraph. Priming makes the model externalize bridging triples for a separate frozen answerer. Reasoning starts from that policy, but removes both explicit insertion and the answerer, testing whether access transfers into normal chain of thought. In stage 1, the trainable policy acts as a graph augmenter. It emits one or more bridging triples, then the frozen base model answers from the original subgraph, plus those triples. The policy never receives target triple labels. It learns only from what its insertion causes downstream. This is the methodological center. The answerer and retrieved context stay fixed, so the inserted set is the only free variable. If the answer flips from wrong to correct, the gain is attributable to the inserted evidence rather than an answerer adapting around weak evidence. Priming does not require a gold explanation or gold bridge. A useful triple is whatever lets the frozen answerer produce the reference answer. This outcome supervision can discover alternative factual bridges, but it also means a plausible-looking insertion is not automatically proven true or mechanistically sourced. Stage 2 initializes from the priming checkpoint and returns the policy to direct question answering. There is no inserted triple set and no frozen answerer. The model generates its own reasoning and final answer from the original sparse subgraph. The sequence tests complementarity. If priming merely duplicates ordinary reasoning optimization, a second reasoning stage should add little. Further gains imply that learning to surface facts and learning to compose an answer are distinct, compatible capabilities. Both stages share an answer quality reward: 60% exact match and 40% token level F1, plus a stage-specific format term. Exact match dominates, while token overlap makes hard multi-hop rewards less sparse. Malformed outputs receive a -1 penalty. For each question, the old policy samples 8 trajectories. Rewards are standardized within that group by subtracting the mean and dividing by standard deviation, plus a small stability constant. Every token in a trajectory receives the same sequence-level advantage. The GRPO objective clips probability ratio updates and penalizes token-level divergence from a stage-specific reference policy. During priming, gradients flow only through the insertion policy. The frozen answerer contributes a reward, but no gradient. During reasoning, the policy is rewarded directly. Each in-distribution dataset supplies about 14,000 training examples and 200 validation examples. Training runs 1 epoch, roughly 500 steps, with batch size 28 and learning rate 1 × 10 to the -6. Priming samples 8 trajectories at temperature 0, 7 with 2, 0, 48 token limits. The main backbones are Qwen2, 5-7b, and Qwen3-8b. Training and in distribution tests use 2Wiki, Hotpot QA, and MooCQA. Mboogle, Natural Questions, Trivia QA, and Pop QA are held out. Every held out result uses only the Hotpot QA checkpoint. GPT-4o judges semantic answer equivalence without seeing graphs or insertions. All baselines receive the same retrieved subgraph and no extra retrieval. Include direct answering, chain of thought, self-ask, recite, unlock with a 72 billion parameter judge, and a matched budget standard GRPO baseline. This controls whether triple activation adds value beyond prompting or ordinary reasoning RL. Priming alone gives the best non-reasoning in distribution average on both backbones. Full VAKE reaches 33, 2 average with insertion plus reasoning on Qwen2, 5 and 34, 9 on Qwen3. Because the VAKE P answerer stays frozen, its gains specifically reflect more useful inserted evidence. Reasoning adds 1, 9 and 1, 7 in distribution points when the insertion pipeline is held fixed. More importantly, direct chain of thought VAKE remains strong without test time triples, showing that the priming checkpoint transferred an access capability rather than merely supplying extra evidence at inference. A Hotpot QA-trained checkpoint transfers to 4 held-out datasets. Direct reasoning VAKE reaches 38, 9 average on Qwen2, 5 and 41, 4 on Qwen3, ranking first across every Qwen3 held-out task. On Bamboogle, Qwen3 rises to 43, 2, 4 points above the strongest baseline. Priming improves nearly every tested Qwen scale from 3 to 14 billion and 0. 6 to 8 billion, the smallest Qwen3 is the exception. Allowing raw documents to condition triple generation helps further, while the frozen answerer still sees only triples. Stronger models continue to benefit from learned activation. The QA gains do not visibly trade away general benchmarks. Across GSM-8K are IME instruction following and MMLU, the base average is 59. 11 VAKE P is 59. 14 and full VAKE is 59. 22. These are near identical, though no confidence intervals are reported. A GPT-4o source judge compares each insertion with the retrieved subgraph. Across all 6 scales, at least 83% are judged non-derivable from that context, with several above 95%. Paper operationally calls these parameter-originated. Useful evidence against copying, but not a mechanistic proof of neural provenance. Mask slot probing asks frozen backbones to reproduce the heads, relations, or tails of correct inserted triples. Larger frozen models know many heads and relations, yet tail accuracy stays at or below 27%. VAKE P reaches 35. 2, outperforming even the frozen 72 billion model on the answer-bearing slot. Removing either stage hurts direct answering. On Hotpot QA, full VAKE scores 43, 4 without priming 31, 9 without reasoning 37, 2 and the base 32, 7. The surprising result is that priming alone still helps direct answers, even though no triples are inserted at test time. Learned skill generalizes across information conditions. With the same insertion pipeline, VAKE improves over base in closed book, triples only, and document-augmented settings. The largest gap is with documents, 46, 6 versus 30. 7, showing activation can complement richer external context rather than compete with it. Important caveats remain. The promise supplement is absent, leaving reward constants, optimizer details, prompts, seeds, and judge rubric undisclosed. There are no confidence intervals or significance tests. Removing answer-containing triples does not prove every retrieved graph is insufficient, and parameter-originated is an LLM judgment, not direct causal tracing. VAKE turns a vague claim, that models know more than they say, into a controlled intervention. First, make candidate knowledge explicit and reward only what helps a frozen answerer. Then remove the instrument and train direct reasoning. The result is a practical bridge from stored facts to testable access.